Simple harmonic motion. Consider a particle moving along a straight line with simple harmonic motion. So if we have a straight line here, and we usually have a central position, and in this case we've called it O, which is quite common. Let's say that D is the amplitude here, and I'm using D just so that if I use A for acceleration we don't get confused. A is very often used for amplitude. And here's a particle which is at the furthest point from the central position. Now if it undergoes SHM, that's not exactly accurate because it would be moving much more slowly out here and more quickly in the middle. Let's now consider it at a position here. We'd measure that distance as x, and x to the right of the central position would be positive, and if the particle were over here, we would have x negative. The particle will accelerate towards the center. So when it's to the right as shown, it will accelerate to the left, and if it were over here, it would accelerate to the right. The acceleration is always towards this central position. The acceleration for simple harmonic motion is always minus a positive constant times x. In other words, it's proportional to the distance from the center. So at this position, the acceleration will be greater than it is here because x is greater here than it is here. Since A is the second differential of displacement, we usually refer to it as x double dot, which just means d2x dt squared. And you'll see when I'm doing examples, I regularly switch from x double dot to d2x dt squared. So what we say is that x double dot is negative omega squared x. Let's just explain that negative. The acceleration is towards the left here, which means it's the opposite to the direction in which x is measured. Since A is equal to dv dt, and using the chain rule, we get that dv dt is equal to dx dt times dv dx, which is, since dx dt is v dv dx. We can also have that x double dot is v dv dx. Let's call this one equation 1 and this one equation 2. The differential equations 1 and 2 can be used to derive equations for an object undergoing SHM and find physical constants such as the period of oscillation. And we'll look at all of this in some examples to follow.